So let's start out first with talking about making sure that you understand what the arrow means. Otherwise, you'll be going the wrong way. So let's take a look at the first problem that was in homework 1. This arrow, got to remember, this is the target and this is the start, or the starting material. So that has to be understood. Otherwise, as I said, you're going to go the wrong way. And I don't know, sometimes there might be a way to actually go this direction, start with this and end up with that, but that's not the point of the question. Maybe some credit will be earned if you do develop a good synthesis for that, but that's not what's being asked. This always means, and even in the homework 1, I think I wrote this, from this. So that's what's actually being asked. How do we approach a retrosynthesis? And what you have to do is you have to look at the starting material. And as I said last semester, if you had me, part of the key is you've got to identify what your starting material structure is. And you got to, at the very least, initially look and see, do I see that in my final product? Now, more often than not, it's going to be there. There are some times where entire bonds might be broken, rings might be opened up, so you have to watch out for that something opens up in the starting material. But in this example, you should be able to see right here, this is clearly the starting material. Now, does that mean that's where these came from? Not necessarily, but at least this is one thing to look out for, because that might be a clue to a good synthetic pathway. Remember, we're trying to simulate what you would do in real life, which is try to solve an unknown problem. So there isn't always a right answer. There's something you're just trying to solve that hasn't been done before. Now, in this case, it's something that I developed from scratch, that there is a distinct answer. You can come up with alternatives. Now, in this case, the fact that you do or should see it twice is that this is a molecule that got added twice to something. In other words, it formed a carbon-carbon bond right here. This formed and this formed between this carbon and the carbon that's right here at the end. Maybe I'll call it carbon A. Doesn't mean anything, the letter A, just to signify. This is the connecting point. And so a carbon-carbon bond making event. We've only learned so far this semester 1, and then we have one from OChem 1. And so from OChem 1, we learned that we can take a alkyl halide, technically primary, and we can add a triple bonded carbon if it was terminal to it. So like this, we can combine these. I don't want to put plus, but we can kind of connect these with a reaction. Arrangement where we add a really strong base to deprotonate this terminal hydrogen on the alkyne, and then that acts as a nucleophile on your alkyl halide. So now, that's not the only way, that's one way. And could we possibly do it? Not really, because in order to do that, we would need to be able to form a triple bond between these two carbons so that this carbon can connect to something. So that's out of the picture. So really, the only other method that we've learned to make a carbon-carbon bond is the Grignard method. In other words, we take a R group that originally is a halide, we add magnesium to it and turn it into a Grignard reagent. And then that's essentially a R-carbanion that can act as a nucleophile. And there's, by this point now, we've learned several, at least 2, I can think of, ways that you can use a Grignard. You can use the Grignard with carbonyls, which I guess you can divide those into 2. You can use them with carboxylic acid derivative type compounds, specifically esters, we've learned. Or you can use them with aldehyde ketones. And then the third way is with epoxides. You can open up an epoxide ring with a Grignard reagent. So right away we can think of the only way that we should realize the only other way that we have to connect this carbon to something is, well, either turn this carbon into one of those carbonyl compounds, or I guess an epoxide, or turn this compound into the Grignard. And what lends us to realize that this is going to turn into the Grignard is that reagent, is that we see it twice, and so we're going to want to add it twice to something. And in fact, if you recall, of those two methods, the initial ones that we called a Grignard reaction, there was the aldehyde and ketone reaction that turned it into an alcohol with an additional R group added to it, or an aldehyde with an additional R group added to it. Or, and this is the one we're going to need, an ester can react. And in the case of the ester, and so this could be Me, it doesn't really matter, because what's going to happen is this falls off. In the case of the ester, we actually add the Grignard R, the Grignard group. We add it twice, if you don't remember, because the mechanism is that the Grignard reagent, we'll call it prime in this case, attacks the molecule twice. Because initially it turns into this compound intermediate with a negatively charged oxygen, like it would normally with an aldehyde ketone. But instead of being moving on to a protonation step, what happens is the oxygen R group, or the OME in this case specifically, is a good leaving group that's actually able to fall off. Put the lone pairs in there. As a double bond oxygen reforms. That's actually the immediate and most likely second step that happens. And so what happens is you form a ketone from an ester undergoing a Grignard without even any addition of water to cause any protonation. And so in other words, this thing that you've now made, that this is turned into, this is still in the presence of Grignard. There's still Grignard reagent present, and so it can attack a second time. And this is where we finally stop and protonate along this mechanism, because now there's nothing else the Grignard, even if you had excess amounts of it, there's nothing in this structure here that can interact with that carbanion. Another R group, another R prime I should say, group with a negative charged I forgot to add my negative charges to these. With a negatively charged lone pair on it. Remember, these R's are carbons in this case. So another carbanion can't come along and attack anything in this molecule. So that's not, this isn't going to play, even if you had it there. So what happens in this last step is you protonate it, and you end up with an OH, a tertiary alcohol, where the two R groups are identical. That's a key point of an ester undergoing Grignard back in chapter 12, is that it added the same R group, which is which comes from the Grignard reagent, twice. So you take an ester and you turn it into a tertiary alcohol with two identical additional carbon chains added to where the ester functional group was located, and now there's an OH group. And that's what we're looking at here. We're seeing that this carbon, the easiest way to add this structure to another chain twice would be if that chain is an ester. So we can easily imagine transforming it, and we'll get to what it is exactly, but transforming this eventually to a alkyl halide that can then undergo first becoming a Grignard in the presence of magnesium and ether, and then finally we take this reagent and add an ester. Once again, it doesn't matter what the thing attached to the oxygen is. It can be anything, but MEO is a pretty standard ester on the single bonded O side, and then double bond O, and then let's look at the chain again that we were using here. It's 1, 2, 3 additional carbons. So 1, 2, 3 additional carbons. And so followed with water. At that point, what you're going to do is you're going to end up with an alcohol. And I'm just going to, well, I'm just going to call this whole thing here R for right now. And so what you're going to end up with is RR added to it. So you're going to add this the starting material twice to the structure, and you're going to end up with an OH. Now, if you remember, what we really want is a BR on here. So the only way that we're going to get an OH to become a BR is one main one that works, and that's just HBr. You learn this, it's via an SN1 reaction, because this is a tertiary alcohol. And so tertiary alcohols very easily undergo substitution with a halide if you use the hydrobromic acid in this case. So that'll finally get you to your final product. So the real question then is, how do we transform this, or how do we get to this? How do we make our starting material become an alkyl bromide, because that's what we need to do this major transformation to the larger tertiary alcohol. How do we make this become an a alkyl halide? If we add HBr to this just straight, we learned in Chapter 8 last semester in OChem 1 that it prefers the Markovnikov addition. The bromine wants to end up on the more substituted carbon, so we can't use just straight up HBr. Instead, we also learned, and we studied I know it was towards the end, so maybe you forgot, that when you have peroxides present, it causes a different mechanism to occur that involves radicals, and in that case, anti-Markovnikov addition occurs. So you can get this by adding HBr, but by also having peroxides, and you can just write peroxides if you want. You can write peroxides, you can say H2O2, you can say ROR, which is just a peroxide that's like hydrogen peroxide, but it has two alkyl groups connected to the oxygen instead of hydrogens. Any of these peroxides would be a good initiator to cause the anti-Markovnikov addition to the alkene that we are starting with. How do we sum this up? Well, I mean, we already have. This is the synthesis, but we can sum it up by writing our starting material, a single arrow going to our final product, and if you want, you don't have to put R groups if that's confusing to you. If you don't know why what I was saying was R, I'll draw what I meant was connected there. And so what I was saying is connected there is our starting material. So the summed up answer would be HBr with peroxides, followed by magnesium in ether, followed by the ester, followed by water, followed by HBr. And that would be how you take this and synthesize this.